What if our universe is just a tiny part of a much bigger multi-dimensional thing? We're going to explore string theory today. And trust me, this is not your average physics class.
I'm all ears.
You, our listeners, have sent in articles and research papers about string theory, and wow, they suggest some wild connections, like between string theory and this thing called 11-dimensional supergravity.
11 dimensions, now that's just showing off.
Right. And then there's the possibility of multiple universes, like what if ours is just one of many?
Right, you've got my attention. Let's break it down.
Okay, first things first. Can tiny vibrating strings really be the building blocks of, well, everything?
That's the million-dollar question, isn't it?
And if so, how could this tiny string theory explain the massive universe?
Good point.
And here's the big one. Does string theory actually mean there's a multiverse? Like a reality where our universe is just one of countless others?
A multiverse.
Trying to explain all the forces of nature in one go.
It is ambitious, but that's what makes it so exciting. It's trying to find a single, elegant framework to describe everything.
And in doing so, it's opening up some pretty mind-blowing possibilities.
Exactly. Possibilities we can't ignore. Well, right now, we understand the universe through two main theories. Quantum mechanics, for the tiny world of atoms and particles.
Right, the really small stuff.
Yep. And then there's general relativity, which is all about gravity and the big structure of the universe.
The big picture stuff.
Exactly. The problem is these two theories, they don't really get along. They seem incompatible, especially when you're talking about extreme places like black holes or even the very early universe.
So it's like trying to jam a square peg into a round hole.
Perfect analogy. And that's where string theory struts in. It suggests, what if, instead of teeny tiny particles, the universe is made of tiny vibrating strings?
Okay, I'm picturing little pieces of string just like bopping around. How does that help us unify physics?
It's all in the vibrations. String theory says different vibrations make different particles and forces. So instead of a different particle for every force, you've got one string that can vibrate in different ways to make all the particles and forces we see.
So like one guitar string can make a bunch of different notes depending on how you pluck it.
Exactly. And just like a guitar string has harmonics and overtones, these strings in string theory can vibrate in complex ways, creating all the different particles and forces in our universe.
Okay, that's starting to make sense. But the articles you sent mentioned something about 11-dimensional supergravity. How does that fit in?
That's where things get really wild. See, the early versions of string theory needed 10 dimensions to work.
10? Already more than I can handle.
I know, right? But then physicists found a potential link between string theory and this thing called 11-dimensional supergravity.
Okay, hold up. 11 dimensions. We only experience 3 spatial dimensions and 1 time dimension.
I know, it's a mind bender. String theory suggests those extra dimensions are compactified, like curled up so tiny we can't see them.
So they're like little hidden pockets of reality tucked away.
You could say that. And what's interesting is that how these extra dimensions are curled up, that can seriously impact the physics we see in our 4-dimensional world.
So the shape of those hidden dimensions determines the tune of our universe, affecting things like what particles exist and how strong gravity is.
Bingo. That's where this idea of strong coupling dynamics comes in.
Yeah, the papers mentioned that, but I wasn't really sure what it meant.
Basically, strong coupling just means how strong the forces are between particles. What physicists have found is that when this coupling is strong, string theories in different dimensions start acting in unexpected ways.
Like they don't follow the usual rules.
Exactly. And those behaviors, they seem to suggest that 11-dimensional supergravity is like the big boss of all the different string theories.
So those extra dimensions we can't even see are messing with the strings in our 4-dimensional world?
That's the general idea. It's like those hidden dimensions are pulling the strings, shaping the physics of our universe.
Okay, I think I'm following so far, but there's still so much to unpack. The articles also mention something called U-duality.
Oh, U-duality. That's a fun one.
It sounds intense. What is it?
Imagine this. All of the different string theories we found. What if they're actually all part of the same, even bigger theory, just viewed from different angles?
So instead of having 5 different string theories, we actually have just one theory that can look different depending on how you look at it.
That's the beauty of U-duality. It's like those optical illusions where the same image can look like 2 different things.
Mind blown. But this raises a big question. If all these string theories are connected, what does that mean for reality itself?
Now that's the question, isn't it? Physicists are still wrestling with that one. But one of the coolest implications of U-duality is that what we think of as fundamental particles and forces, maybe the lines between them are blurrier than we thought.
You mean like even the most basic building blocks of reality could be subject to this duality thing?
Exactly. What we see as different things might just be different sides of the same fundamental string, maybe vibrating differently or hanging out in different dimensional arrangements.
Okay, U-duality sounds like a key to a deeper understanding of how string theories are connected. But how does it work in practice? I vaguely remember something about mapping class groups and different types of degenerations
Ah, yes. Remember how we were talking about compactifying those extra dimensions?
to get to our four-dimensional spacetime.
Right. Well, how we choose to do that compactifying, it can really change the physics we end up with. Different compactifications can lead to different particles, different forces, the whole shebang.
So like those hidden dimensions are a giant canvas, and how we fold that canvas affects what we see in our four-dimensional world.
Beautiful way to put it. And mapping class groups, they're like the rules for how we can fold that canvas without ripping it. They describe the different ways we can change the shape of those compactified dimensions without messing up the overall structure.
So we're talking about like twisting and stretching those hidden dimensions, like playing with a piece of cosmic Play-Doh.
Kind of. And as we do that, we can hit these things called degenerations. That's where the physics of the string theory simplifies in certain ways. It makes it easier to study and learn about its underlying structure.
So by studying those degenerations, we can figure out how different string theories are linked and how they might all fit together into that 11-dimensional theory.
Exactly. And here's the kicker. There's only a limited number of ways those degenerations can happen, which gives us a way to categorize and understand the connections between string theories.
Okay, my brain is doing backflips. Maybe we should take a breather and recap what we've learned so far.
Good idea. We have covered a lot.
We started with the idea that string theory could be the key to unifying physics, bringing together quantum mechanics and general relativity. Then we jumped into the deep end with 11-dimensional supergravity, this mysterious framework that might hold all the string theories together.
We did, didn't we? And don't forget U-duality, that mind-blowing idea that all these different string theories might just be different sides of the same coin.
Right, different perspectives on the same underlying reality. And we even touched on how mapping class groups and degenerations give us a way to study and categorize all these different string theories.
Uncovering a deeper level of structure within the universe, it's quite a journey. And we've only just begun to explore the possibilities.
I'm already feeling like I've taken a crash course in theoretical physics. But there's still so much more to explore. I'm particularly interested in those BPS-saturated particles and how they might be connected to dark matter.
Oh, that's a good one. And it ties in perfectly with some of the other things we've talked about, like the strong coupling dynamics of string theory.
All right, then let's jump back in. Tell me more about these BPS-saturated particles. What makes them so special?
Well, the key thing is they show up in a very specific way within string theory. They come from these things called BPS states, which are basically really stable arrangements of strings.
Stable arrangement. So it's like these strings are stuck in specific patterns. They don't easily unravel or change.
That's a good way to visualize it. And what's remarkable is that these BPS states often keep some of this thing called supersymmetry, which is a concept that links particles with different spins.
Okay, supersymmetry. I think we've touched on that in some previous deep dives. It's that really elegant idea that could unify matter and forces at a fundamental level, right? But what does it have to do with these BPS states and these mysterious particles?
So supersymmetry, it kind of sets some strict rules for particles. Like, it predicts that for every particle we know, there should be a supersymmetric partner with a different spin.
Oh, right, like a selectron for every electron, a squark for every quark. But we haven't actually found any of those supersymmetric partners, have we?
Not yet, no. But that doesn't mean supersymmetry is wrong. Maybe these supersymmetric partners are just super heavy, too heavy for our current experiments to see.
So supersymmetry could still be hiding out there, even if we haven't seen it directly. But how does this connect back to the BPS states and those BPS-saturated particles?
The link is that BPS states often protect some of the supersymmetry of the theory. Even if supersymmetry is broken at low energies, like it seems to be in our universe, it can still hang out within these special BPS configurations.
So BPS states are like little pockets where supersymmetry is still alive and kicking. like tiny sanctuaries for this hidden symmetry.
Exactly. And the particles that come with these BPS states, the BPS saturated particles, they inherit some of the special traits of supersymmetry.
Like that specific relationship between their mass and charge you were talking about earlier.
Yep, that's the one. It's called the BPS bound, and it comes directly from the math of supersymmetry. It basically makes sure these BPS saturated particles don't decay into other particles easily. It makes them incredibly stable.
Stable, and maybe not interacting much with normal matter. That's starting to sound like a good candidate for dark matter.
Right. That's why a lot of physicists think BPS saturated particles could be the missing pieces of the dark matter puzzle. They're stable, they don't interact much, which explains why we haven't seen them directly, but they still have mass, so they could still be causing those gravitational effects we see.
Okay, this is all starting to click into place. But how do we actually find these particles? If they hardly interact with anything, wouldn't they be incredibly difficult to detect?
It's definitely a challenge, but physicists are coming up with some really clever ways to try and find them.
Like what? What are some of the strategies?
Well, one approach is to look for indirect signals. If dark matter particles are really these BPS-saturated things, they might annihilate each other sometimes, and that would create stuff we can see, like gamma rays or neutrinos.
So we look for these telltale signs and data from space, like from telescopes looking at galaxy clusters or the cosmic microwave background.
Exactly. There are actually experiments going on right now that are looking for those signals, hoping to find the smoking gun that points to BPS-saturated dark matter.
That would be a massive discovery. Imagine finally solving one of the biggest mysteries in cosmology.
It would be huge, and it would really show how powerful string theory is, guiding us to new frontiers in our understanding of the universe.
Speaking of new frontiers, the papers mentioned something about BPS-saturated particles having this weird mass scaling. What does that mean?
That's a really cool feature. It has to do with how their masses change as you adjust the string coupling constant, which is basically the knob that controlled how strong interactions are in string theory.
Okay, so we're talking about turning the knob that controls how strongly strings interact with each other. Makes sense.
And what physicists have found is that the masses of these BPS-saturated particles, they change in a really different way compared to normal particles.
How so? What's the difference?
Well, with regular particles, their mass is usually inversely proportional to the square of the string coupling constant. So weaker coupling, heavier particles, and vice versa.
Okay, that makes sense. Weaker interactions, heavier particles.
But BPS-saturated particles, their mass scaling is way more chill. It might be inversely proportional to the coupling constant itself or even completely independent of it.
Hold on, so these particles could stay pretty light even when the string coupling gets really weak.
That's exactly it. And that has some pretty big implications. For example, it suggests that BPS-saturated particles could have been a big deal in the very early universe, when the string coupling was probably a lot stronger than it is now.
I get it. So even though they might be rare now, back then they could have been super abundant, maybe even making up most of the energy in the early universe.
Exactly. And that could have had a big impact on how the universe evolved, maybe influencing things like inflation or the formation of those large-scale structures we see today.
This is all mind-blowing stuff. So let's recap again. We've explored how string theory could potentially unify physics. We've encountered extra dimensions, this mysterious 11-dimensional supergravity. We've even dug into these BPS-saturated particles that might explain dark matter. But where do we go from here?
Well, all of this leads us to one of the most mind-bending implications of string theory, the possibility of a multiverse, a reality where our universe is just one of countless others, ready to go down that rabbit hole.
Absolutely. Let's take a quick break and then dive into the multiverse.
Okay, so the multiverse, it's a pretty wild concept, right? The idea that our universe is just one of many others out there.
It definitely bends the mind a bit. But before we go full-on multiverse, I wanted to circle back to something you said earlier.
Yeah.
About how those extra dimensions in string theory, the way they're compactified, can actually change the physics we see.
Ah, yes. That's a really important point. It's like having this set of building blocks and then a whole book of instructions on how to put them together. The building blocks are the fundamental strings and those instructions. That's all the different ways those extra dimensions can be compactified.
So each way you fold those dimensions creates a different universe with its own unique physics.
Exactly. It's a beautiful idea, really. And that's where those mapping class groups we were talking about come in. They give us the mathematical language to describe all those different ways to fold those extra dimensions without tearing the fabric of reality.
So mapping class groups are like the rule book for building a universe.
Yeah, you could say that. And by exploring all the different rules, we can start to imagine all the different kinds of universes that might be out there.
Okay, so let's talk about those possibilities. You mentioned that string theory might point to the existence of a multiverse, a whole bunch of universes existing alongside our own.
That's right. String theory has this enormous landscape of possible solutions, what we call vacua. Each vacuum represents a different set of physical laws and constants, which could create a whole different universe. Imagine a giant cosmic library filled with books, and each book describes a different universe.
A library of universe. That's amazing. But if there are all these other universes, wouldn't they be totally cut off from ours? Like completely inaccessible?
For the most part, yeah. But there are some really cool ideas about how we might be able to detect them indirectly. Think of it like two ships sailing on the ocean way too far apart to see each other.
Okay, I'm picturing it.
They might never actually lay eyes on each other, but they could still sense the other one's presence. Maybe by noticing subtle ripples in the water or faint echoes carried on the wind.
I like that analogy. So
Yeah.
how could we detect those ripples or echoes from other universes? What would we be looking for?
Well, one possibility is that our universe might have bumped into another universe a long, long time ago.
Like a cosmic fender bender.
Exactly. And that collision could have left behind a kind of imprint in the cosmic microwave background radiation, the afterglow of the Big Bang.
So it would be like a faint bruise on the fabric of space-time, a mark from that ancient collision.
You got it. And some physicists think they might have actually found some weird stuff in the CMB data that could be explained by this. But it's still early days. The evidence isn't super strong yet.
Wow, that's incredible. So we might already have a glimpse of another universe. Are there any other ways we could detect these cosmic ripples?
There's another thought out there. If those other universes are close enough to ours, their gravity could be tugging on things in our universe, just a little bit. Kind of like how you can tell a planet is there even if you can't see it, just by how its gravity affects other planets.
So we could see the shadow of another universe through its gravity. Are scientists looking for that?
Oh, yeah, absolutely. There are definitely folks out there looking for these tiny gravitational anomalies. It's not easy, though, and the evidence we have so far is super subtle.
Okay, so maybe we can't book a trip to these other universes anytime soon, but we might still be able to sense them. What do you think these other universes would be like? Would they be anything like ours or totally different?
That's one of the big mysteries, right? It's possible that some of these universes are pretty similar to ours. Maybe gravity is a bit stronger, or the electron is a bit heavier.
So a universe where you'd weigh a bit more or electricity works a bit differently.
Right. And it's not impossible that there are universes out there where life could exist, maybe even intelligent life. Maybe they're even thinking about other universes just like us.
That's a wild thought. But what about universes that are totally different from ours? What kind of crazy stuff could be going on out there?
Now that's where things get really interesting. There could be universes with completely different forces, particles, physics we can't even imagine. Think of a universe where time runs backwards or gravity pushes things apart instead of pulling them together. The possibilities are endless.
Okay, my brain is officially melting down. Is there any way to narrow down those possibilities, to focus our search for evidence of the multiverse?
That's a good point. It can get overwhelming. One way is to look for things that a lot of multiverse theories have in common. For example, many of them predict these things called cosmic strings.
Oh yeah, cosmic strings. I've heard of those. They're like giant cracks in space-time, right?
That's a pretty good way to picture them. And they could have a big effect on how the universe evolves. Like maybe we could actually see signs of them.
So we should be on the lookout for these giant cosmic strings.
Exactly. Imagine them like invisible tripwires stretched across the universe. If we find them, that would be a pretty big hint that we're living in a multiverse.
Okay, so cosmic strings are one thing to look for. Any other promising leads in the search for the multiverse?
Another really exciting area is black holes. Some physicists think black holes might be like gateways to other universes.
Wait, are we talking about actually traveling to another universe through a black hole?
Yeah.
That sounds like something out of a sci-fi movie.
Haha. Yeah, it does. And that's probably way beyond anything we could do with our current technology. But even if we can't actually go through a black hole, studying them might still give us clues about the multiverse.
Okay, I'm down for exploring the multiverse, but I think I'll skip the black hole trip for now. So, what could we learn from black holes about other universes?
Well, some physicists think that when black holes evaporate, which Stephen Hawking predicted they do, They might leave behind little traces of other universes.
So the ashes of a black hole could contain hints of the multiverse. That's mind-blowing.
Right. It's a really cool idea. And those traces might be detectable in the cosmic microwave background radiation or other things we can observe in space. It's like looking for a needle in a haystack, but the payoff could be huge.
This deep dive is really taking us to the edge of what we know about the universe. It's amazing to think we might be close to finding proof of other universes.
It really is an amazing time for this kind of research. And even though the evidence for the multiverse is still mostly indirect and kind of speculative, the fact that serious physicists are taking these ideas seriously shows just how much string theory is changing how we think about the universe.
Okay, before we get lost in all these parallel universes and cosmic strings, I think we should come back down to Earth for a minute. Didn't the papers say that string theory could also have implications for stuff in our everyday world?
Oh, absolutely. String theory might be all about the fundamental nature of reality, but it's also making its way into other areas of physics, like condensed matter physics and even nuclear physics.
Really? I'm surprised a theory about tiny strings in 10 or 11 dimensions could be useful for stuff like that. Tell me more. How does that work?
Well, a key concept from string theory is this idea of duality. Remember how we talked about U-duality, connecting all the different string theories?
Yeah, it's like different perspectives can reveal hidden connections, like how one object can cast a bunch of different shadows depending on where the light is.
Perfect analogy. And it turns out that duality isn't just for string theory, it can be applied to other areas of physics too. It gives us new ways to think about and solve really complex problems.
Okay, I'm following. Give me an example. How could you use string theory to study something like condensed matter physics? That's the study of materials at super low temperatures, right?
Right. Well, in condensed matter physics, people are using string theory to understand things like superconductivity. That's where materials can conduct electricity with zero resistance.
Wow. So string theory could help us make more efficient power grids or better batteries.
That's the hope. By using the tools and ideas from string theory, physicists are finding new connections and patterns in condensed matter systems, which could lead to some pretty cool new technologies.
That's incredible. String theory isn't just about these abstract ideas. It can actually lead to real-world applications.
You got it. And it doesn't stop there. String theory is also being used in nuclear physics, which is the study of the nucleus of an atom and the forces that hold it together.
Whoa, hold on. How does a theory about tiny strings in 10 dimensions connect to the nucleus of an atom?
It does seem like a strange connection, but the thing is, the strong force, which holds quarks together inside protons and neutrons, is super hard to study at low energies using our normal methods.
Right, it's like trying to untie a knot that gets tighter the more you pull on it.
Exactly. But string theory offers a new way to tackle this problem. It's called the add-SCFT correspondence. It basically connects a theory of gravity in a higher dimensional space to a quantum field theory in a lower dimensional space, so we can map the strong force onto a theory of gravity.
Wait, so you're saying we can understand the strong force, which governs those tiny quarks, by studying gravity in a higher dimensional universe? That's like using a mirror to understand the object itself.
That's a great way to think about it, and the cool thing is this correspondence allows us to do calculations in the gravitational theory, which is often way easier, and then translate those results back to the strong force, like having a secret decoder ring for the strong force.
So it's like a cosmic cheat sheet for nuclear physics. Has this approach actually worked?
It has. Physicists have already learned some surprising things about the strong force using this method. It could help us understand nuclear matter way better, and even the processes that power stars and supernovae.
This whole deep dive has been incredible. We've gone from the smallest strings to the vastness of the multiverse and back down to the heart of the atom. I feel like I've learned so much. But I have to ask, you mentioned that string theory is still a work in progress. What are some of the biggest challenges facing string theorists right now?
Great question. Probably the biggest challenge is figuring out how to test string theory experimentally. A lot of its predictions involve energy scales that are way beyond what we can do with our current technology.
Right, like those cosmic strings or the gravitational pull of other universes. We'd need some serious tech upgrades to directly study those things. It's like having a map to a faraway land, but no way to actually travel there.
That's a good way to put it. But, physicists are always pushing the boundaries of what's possible, both with experiments and with our theoretical understanding. There's always hope that we'll find a way to test string theory in the future, maybe through some clever indirect observations, or by developing new technologies that can probe those high energies.
So there's still hope for testing string theory someday. That's good to hear.
Absolutely. And in the meantime, string theory is still an amazing source of new ideas and ways of thinking about the universe. It's giving us new insights into the nature of reality and pushing us to think beyond what we thought we knew.
Well, I'm definitely inspired. Even if we never managed to directly test string theory, it seems like it's already had a huge impact on physics and math.
I completely agree. String theory has opened up whole new areas of research, shown us connections between things that seemed totally separate before, and inspired generations of scientists to think bigger and bolder. Who knows what else it might reveal in the future? It's an adventure that's still unfolding.
I can't wait to see where this adventure takes us. But I think we need to take a break from all this mind-bending physics for now. Let's gather our thoughts and then come back to wrap up our exploration of string theory and its implications.
Welcome back. Ready for round 3 of our string theory deep dive.
My brain is still buzzing from our last chat, but yeah, let's do it. That multiverse stuff, it's a lot to take in.
It is, isn't it? It really challenges how we think about reality.
So we were talking about the possibility of all these other universes out there. But if there really are so many, how do we even begin to understand them? Is there some way to organize them, like put them into categories?
That's a big question, and a lot of smart people are working on it. One way to think about it is to focus on the features that make each universe unique. Kind of like organizing a collection of stamps, you know? You might group them by country or year or theme. We can do something similar with universes, looking at their key characteristics.
Okay, so what kinds of characteristics could we use to classify universes? Would it be things like what kinds of stars and galaxies they have? Or maybe even whether there's life in them?
Those are definitely interesting things to think about. But from a string theory perspective, we might start with even more basic things, like how many dimensions a universe has, or the value of its cosmological constant.
Right, we talked about those extra dimensions that string theory predicts, and how they're usually curled up so tiny we can't see them. But what if they weren't curled up? What would a universe with like 5 or 6 spatial dimensions even look like?
Now that's a real head-scratcher. The laws of physics would probably be totally different in a universe like that. It's really hard to even imagine what kinds of structures or phenomena might exist beyond our 3-dimensional world.
So it's like trying to picture a new color that's not on the color spectrum, a concept we can think about, but not really grasp.
Exactly. And that's part of what makes the multiverse so fascinating. It forces us to think beyond the limits of our own experience and consider things that might seem totally alien to us.
Okay, so the number of dimensions is one way to categorize universes. What other features could we look at?
Another big one is the value of the cosmological constant. That's that mysterious energy that's all throughout space, affecting how fast the universe expands.
Right, we talked about that when we did our deep dive on dark energy. The cosmological constant is this huge puzzle. It's incredibly tiny, but not zero. And it has a huge impact on what ultimately happens to the universe.
Exactly. And in a multiverse scenario, different universes could have different values for their cosmological constant. Some might be expanding really fast like ours, while others might be shrinking or even staying the same size.
So you can have this crazy mix of expanding, contracting, and static universes, like a cosmic patchwork quilt of different realities.
That's one possibility, and it raises some interesting questions about the anthropic principle, the idea that the universe is fine-tuned for life to exist.
Oh, right, the anthropic principle. If there are tons of universes out there, each with its own unique set of properties, it makes sense that only a few of them would have the right conditions for life to arise. So maybe it's not so surprising that we find ourselves in a universe that seems perfect for us.
That's one way to look at it. The multiverse could explain why our universe seems so fine-tuned without having to resort to any special explanations. It could just be a matter of probability. If you have enough universes, some of them are bound to be just right for life.
That's a mind-blowing thought. It kind of takes the pressure off trying to figure out why our universe seems so special. But let's not forget, we still haven't proven that the multiverse actually exists. It's a really cool idea, and it fits with string theory, but it's still very speculative.
True, but as we talked about earlier, there might be ways to find evidence for other universes, like those subtle hints in the cosmic microwave background radiation, or maybe even strange movements of objects in our universe.
Right, and we also talked about cosmic strings and black holes as potential windows into the multiverse. But those are really tough observations to make. It's like trying to assemble a puzzle with only a few pieces.
It's definitely a huge challenge. But trying to understand the multiverse is one of the most exciting and important frontiers in physics today. It's all about unraveling the biggest mysteries of the universe and figuring out where we fit in.
Well, I'm definitely on board for this journey. I can't wait to see what new discoveries come out of this research in the next few years. It feels like we're on the verge of some major breakthroughs.
I agree. It's an incredibly exciting time to be working on this stuff. Who knows what amazing things we'll find as we keep exploring the universe.
Well, on that note, I think we've reached the end of our deep dive into string theory and the multiverse. What a wild ride. It's been amazing to explore these mind-blowing concepts and all the incredible possibilities.
It's been a pleasure chatting with you. I hope this has sparked your curiosity and made you want to keep learning about the universe.
It definitely has. I have a feeling we'll be revisiting these topics in future deep dives, especially as new discoveries are made. In the meantime, keep looking up and never stop asking those big questions.
Couldn't have said it better myself.